Hello and welcome to CSC 228. Today we have a special guest lecture from Kevin Laeufer on formal verification. So, to give you a brief background on Kevin. Uh, he did his PhD recently at UC Berkeley, completed it. He's now a research associate at Cornell University, continuing to work on open source hardware tools and making that process more agile and efficient. Much of his PhD work involves some form of testing and verification of hardware. And so for today, to tell us about his work on making formal verification available in Chisel, that's a really cool thing he's done. He's created this lecture. He's now given, I believe, 3, maybe 4 times in this course. So I'm really grateful for his contribution to this course and this community. And you can see that, like in the other lectures for this course, this is a live Jupyter notebook. He's going to be running code today. And for students in the course, in case you forgot, we do have a Lab 6 based on this. That'll be posted later today and due in a few days. Also, Kevin, amongst the duties of the grad students, spent some time maintaining Chisel tests. Of course, that library we're so enamored with and dependent on for this course. So with that, I'm very happy to welcome Kevin to give this guest lecture.
Thank you so much for the introduction. Yeah, I think almost everything has been said. So I made these slides like a couple of years back because I was like, hey, I added formal verification to Chisel test, and it would be nice for students to get some hands-on experience with that, because formal verification has kind of had this little, it's kind of been like a niche subject in some ways because, it was like a pretty big research subject like 20 years ago, and then people went into industry, made commercial tools, and all those commercial tools are just really expensive. And so unless you work at one of those big companies, it's really hard to get your hands on even like the tool that you would need to do formal verification. But that has changed recently. There's been some work to enable formal verification for Verilog designs with Symbiosis, which is like an open source tool that you can use to verify Verilog designs. And inspired by that, I basically added some of this a similar approach to the Chisel test library. So this essentially makes it like super easy to get started on formal verification. Of course, potentially the commercial tools can handle bigger designs, can handle like larger problems, but all of the principles kind of remain the same. And so yeah, if you want to, you can follow along those slides at home. If you have been able to run all the other slides, it should just work. The only major difference is that you should also have this Z3 SMT solver installed. And we'll learn in a minute what SMT means and what an SMT solver does. Not exactly how it works, but kind of the tasks that it's solving. But yeah, this SMT solver is pretty available. So whatever your package manager or whatever your system, you can probably install it. Yeah, so what's the plan for today? So basically, the idea is I want you all to go away with a decent understanding of what formal verification for circuits entails, at least the kind of formal verification that I've been working on, which is verification based on Boolean satisfiability and SMT. And we'll also learn what those two terms mean. And then we'll learn sort of like what are the differences between combinational or combinatorial circuits and sequential circuits, and how does the verification for those differ? What are sort of the guarantees that we get after formally verifying? And we'll also like look at some practical examples just to see what the difficult parts are and like what the power is of formal verification. Okay, so let's start with the basics. And the basics are, well, first of all, we need to import all our code, which I've already done here. So all of this code, you can look at it if you want to, but you don't really need to look at it. It's mostly there to allow me to write more like shorter expressions that actually fit on my slides. So if you want to see what the magic is in the background, you can look at that code, but it shouldn't be necessary to understand this lecture. So the first thing I want to talk about is the Boolean satisfiability problem. And so what does that problem mean? So the problem says that we have some formula, some Boolean formula. That means that all the inputs to this formula, all the variables, are Boolean themselves. So x1 through xn is each one of those can be assigned to either true or false. And also evaluating that formula will give us a Boolean result, so either true or false. And so now the Boolean satisfiability problem, it asks, can f ever evaluate to true? Or another way of framing this or phrasing this is, does there exist an assignment to the variables x1 to xn such that f evaluates to true? And if that exists, then we say that f is satisfiable, or for short, sat. Or the other possibility is that there's no possible assignment to x1 to xn such that f evaluates to f evaluates to true, or to phrase it the other way around, all possible assignments for x1 to xn make f evaluate to false. So you could brute force basically all possible combinations of true and false for x1 to xn, and every time you plug those in, evaluate f, you get false. And that means it's unsatisfiable. And so every Boolean formula is either satisfiable or unsatisfiable. Now we have this little helper function here, which we'll call the SMT solver in the background, and we'll get more about what SMT means later. But basically what it will do is it will take a Boolean formula and it will tell you whether it's satisfiable or not. And so we have here the formula B0 and not B0. Now think about it. What are the possible assignments to the variables in this formula? Or what are even the variables? The variables are B0. There's no other variable in there. And so if you only have one variable, there are only two possible assignments. It's either true or false. And so now you could brute force this. You could say, okay, what if B0 is true? What's the result? The result is 0. What if B0 is 1? Well, the result will also be 0. And so that means for all possible assignments, the formula evaluates to 0, which in our case means false. And so that means that the formula is unsatisfiable. So let's try to run this. And we'll see that, yeah, okay, there's a deprecation warning, which is fine. But anyways, so this is the actual result that we want, which says that this formula is unsatisfiable. Okay, that's exactly what we thought, right? So now let's look at the next formula. This one has two variables, right? So the variables are B0 and B1. So now how many different assignments are there? There are 4 different assignments, right? 2 to the power of 2. Meaning that either B0 and B1 could both be false, they could both be true, one of them could be 0 and the other one could be 1. So basically, there are 4 different assignments. And now we can think about, is there any assignment for which this formula evaluates to true? And well, if you think about it, there is, right? So if B0 is 1 and B1 is 1, then the ANDing together those two values becomes 1. Just as a side note, I'm like using true and 1 kind of interchangeably here, and 0 and false, just because that's kind of how it also works. If you're verifying hardware, it's basically the same thing there. And so in this case, we'll see that, oh yeah, our function actually says that this formula is satisfiable, and it will provide us with an example. So if a formula is satisfiable, you can always have one example that sort of proves that it's satisfiable, because we only need one example to show that the formula is satisfiable. For a formula to be unsatisfiable, you actually need to say something about all possible assignments. So there's not just a single example that you can show in order to prove that it's unsatisfiable. Now, we have one more formula here, which also has 2 variables. And you can think about sort of a little bit on your own. What are possible assignments that would make this formula true? Does there exist such an assignment? And you might have come up with this, well, there's like actually 3 different assignments. And now we'll see which one we get. And so we get the one where B0 is 1 and B1 is 0. Because the solver basically has some freedom to choose which one it wants to pick. And in this case, it chooses this one. So that's the Boolean satisfiability problem. I kind of just want you to understand right now, what is this problem? What are we trying to determine? What are the possible answers, right? And now we can think a little bit about, how is the solve function actually implemented? What do we need to do to determine satisfiability? Now, one thing we can do is we can write down a truth table, right? So if we have this formula saying B0 and not B0, that was the first one that we're looking at, we can write down a truth table. It has 2 entries. And then we see all the column on the right-hand side is always 0. So that means this formula is unsatisfiable. For the next formula, which is the same formula we had before, where it's B0 and B1, we can also write down a truth table. And we can see that there is one row where it results in 1. And so that means that there exists an assignment for which this formula is true, and so it's satisfiable. And because we found the row for which this is true, we can just like look into this row and see what assignments are, and we already have our example to prove that it is satisfiable. Now, some of you might have noticed what the big problem with this is, right? Like, think about, what's the problem with always writing down the truth table? Just take like 10 seconds, and then I'll tell you.
It like scales really fast.
Right. It scales very poorly. So it scales with like 2 to the number of variables, essentially. So you get like a huge truth table if you even have like a couple of bits. And now if you think about your circuit, you can think of it like as a first order approximation. You can say like, oh, we need 1 bit for every input bit to our circuit. So if our circuit has like, you know, 2 32-bit inputs, then that means we need 64 bits, 64 input variables. And that already is a humongous truth table that won't ever fit into the memory of your computer. So as we've noticed, this Boolean satisfiability problem, it can be solved with a truth table. But the problem is that the truth table size grows exponentially with the number of variables. And so this problem was identified as the first NP-complete problem, meaning that it has this sort of worst case complexity that's really bad. But one thing that happened after it was identified, well, the thing that happened after it was identified as like a really hard problem is people kind of were giving up on it. We're saying like, okay, this is impossible to solve algorithmically. We should just never attempt. But then a couple of decades later, researchers actually started being like, okay, but what we know a lot about the worst case complexity, but what about the average case, like the cases that we actually care about? And so one thing they did is they just like generated a whole bunch of random Boolean formulas and just tried out an algorithm that they came up with and saw how long it would take. And it turns out, well, there are cases where the algorithm just takes forever, essentially. But there are also a lot of cases where it finishes within a reasonable amount of time. And so what this tells us is only because something has like a really bad worst case complexity doesn't mean that it's impossible to solve. And it actually turns out that there are a lot of interesting cases where this particular problem can be solved relatively quickly. And ever since like the 1990s, people have basically been working on better heuristics to more quickly solve a lot of common problems in Boolean satisfiability. Now, this is Boolean satisfiability. So you have a formula that takes basically 1-bit variables as input and it evaluates to 1 bit. Now, SMT means it's a satisfiability modulo theory. So essentially, we add a more expressive language essentially to our Boolean satisfiability problem. And why would we want to do that? Well, we want to do that because if we think about our hardware designs in Chisel, we don't just work on individual bits. We don't like build our adders directly from NAND gates, even though it might end up as something like that on the actual circuit. But we actually like talk about more high-level things like addition and subtraction and module operator shifts and things like that. And so SMT basically provides a richer language to express some of these high-level ideas. And so the things that we're actually most interested in for hardware verification are bit vectors, which is modeling fixed bit width integers. So you can think about it like in C, for example, your int is normally 32 bits, and so you might represent it as a 32-bit bit vector. And in Chisel, your uint and sint can be any bit width that you want it to be, and so this also then maps to like a bit vector of this particular bit width that you chose. The other thing that is kind of interesting to us are arrays, which allow us to model storing and loading from memory. So basically, it's kind of a map from index to data, where we can basically insert things and then retrieve things later. And so this basically means SMT to us is just like a high-level language in which we can kind of express these ideas from circuits more directly, and then the solver can sort of do its magic to try to solve a formula that involves these more richer data types. And so here I have an example. We're basically trying to solve a plus a is equal to 8. So we have this variable a, and we say, okay, add a and a together, and it should equal and the result should equal to 8. And the question is there a solution for a that satisfies this formula? So you see here a is a wider bit vector. I don't actually write down what it is here, but I think it's 32-bit or something like that. It's defined somewhere earlier in that big code snippet that I skipped. But then basically, you see the result of this formula is still Boolean. So we have richer input variables, but we still want to have something that is a statement, a propositional statement. And so now if we execute this, the solver will actually say, yes, this is satisfiable, and a should equal to 4. And we can think about this, right? 4 plus 4 is equal to 8. So that's great. Now, the next thing I want to know is there a way to choose a such that a plus a is equal to 9? Now, think about this a little bit, and then I'll tell you what's going on here. The basic question is like, right? Like if you think about it, from like a math background, you say like, okay, a plus a is equal to 9. So 2 times a is equal to 9. So a is equal to 9 over 2. However, a is supposed to be a bit vector, meaning like an integer, right? And then if you think about it that way, you realize that there is no integer solution to this problem. And so basically the solver will say that it's unsatisfiable. Now, the last little thing that I want to do here is I want to like try to come up with this standard compiler optimization, which is where we're saying like, okay, we have some variable c that's multiplied by 4, and we should be able to do a strength reduction where we turn the multiplication into a shift. And now we're just searching for this a because we want to basically know what is there an a for which this is equivalent. And so we can actually put this into this SMT formula, basically just transcribing this thing, and it will say, oh yeah, if you choose a to be 2, then if you multiply this constant that we chose, this random constant, by 4, then it's the same as shifting that constant by 2. And that makes a lot of sense here, right? Now, the next question is, can we do the same thing if we're multiplying by 5? So you can think about it for a second or two in your head, and then I'll run it. And you'll see, no, it's unsatisfiable, right? Basically, there is no constant such that we could do this shift. And that makes sense because you might know that this strength reduction only works for power if you multiply with a power of 2. So 4 is 2 to the 2. 5 is not 2 to anything. If you want to, or at least if we're looking only at integers, what's the next power of 2? The next power of 2 would be 8. So we could put an 8 here. And lo and behold, we'll actually get a is equal to 3. So in that case, it works again. Okay, so that's it for bit vectors and SMT, or SMT and Boolean satisfiability. Are there any questions at this point?
Any questions? Okay, I'm getting nods. We're good.
Okay, that's great. Now you might be asking, okay, you told me about all this like SMT and Boolean satisfiability stuff, but what about circuits? We're like an Agile hardware design class. Well, now we're going to try to bridge the gap between circuit and this whole like SMT and Boolean satisfiability business. What's the connection, right? First of all, we're going to look at combinatorial or combinational circuits, meaning circuits that don't have any state elements, so no registers and no memories. Okay, and so those circuits, if they have an assertion in them, that can be directly mapped to an SMT formula. So what does an assertion mean? Assertion, basically, there's like this assert statement in Chisel, and what it basically does is just says like, okay, this should always be true. And if during simulation, for example, you somehow manage that B is not greater than A, then the simulation will stop and say, hey, this assertion was violated. And these assertions can also be used for formal verification. So what is the circuit that we're describing here? This is just a snippet. It's not a full Chisel circuit. It's saying that there is some A, which is an input. So this means it's basically like a free variable. Like earlier, we were saying, oh, there's like B0 and B1 that are inputs to this formula. And that's kind of what we're doing here. We're saying like there's an input to the circuit, becomes an input to the formula. And now we're saying there's a B that's equivalent to A plus 1. So B is not actually just a free variable. It's just like A plus 1. And now we're saying B should be greater than A, which means if we just plug in B here, it means that A plus 1 is greater than A, okay? And now we want to verify that using an SMT solver. So what do we have to do for that? Well, an SMT solver basically gives us an assignment. And so we're thinking like, what kind of assignment are we interested in? And the kind of assignment that we're interested in is an assignment that shows us that this is false, right? Because if such an assignment exists, then we know that there is a bug. If no such assignment exists, or no assignment exists that will make the assertion false, then we know that the assertion will always be true. Okay, so how can we encode that? We can say, okay, there is a B that's equal to A plus 1, and now find us a thing where B is not greater than A. So we're inverting it here because we're trying to see if the assertion can be violated. And now we can try to ask the solver. You can also think about it for a second or two, and then I'll start it. And what does the solver say? The solver says there is actually such a situation. There is a situation in which A is equal to this big number, and then B is equal to 0. Now, why is that? Those of you familiar sort of with the computer arithmetic might have realized already that, well, we are running into an overflow problem. And to see that a little better, we can like use these two prints. So what I'm doing here is basically I'm converting this big number that a is supposed to be to a binary string. And then I'm converting the a plus 1 to a binary string. And here you'll see that a is basically like all ones, of all 32 ones. And the b is basically plus 1. And you know, in Chisel, if you do an addition of two things that are 32 bits, then the result will also be 32 bits, and the highest bit will be discarded. There's a ampersand plus if you actually want to keep the highest bit. But in this case, it gets discarded, and so basically b ends up being just this, which is 0. And 0 is obviously not greater than this number. And so that's what's happening here. Okay. Now, this is the same example that we had before, just now with actual Chisel. So before, I was showing you how can you transcribe manually this circuit idea into an SMP formula. And now here is basically just a Chisel circuit, and we are using this verify command, which is imported from Chisel test. And so what this does now is it will actually generate the fertile from Chisel, and then from the fertile, it will generate an SMT formula that then gets handed off to an SMT solver, and then we get the result. And we see that in a Chisel assertion, we can actually also print out the values of A and B when this assertion fails, so we don't need to do anything special here. And so now we're running this. It takes a little bit more time. And we see here, we found an assertion violation, and it will actually print out what happened. It says 1111111 is not greater than 0. And basically, it finds the exact same situation that we found earlier. So this B here makes it be formatted in binary. And so yeah, this is how you can do it with Chisel. Now, there is this whole issue of like, why are we doing bounded check 1 here? And we'll get into that later. The bounded check thing is only really important for circuits that have state, that have a memory or a register. But we need to always supply it. But for combinational circuits or combinatorial circuits, bounded check 1 is always sufficient. Okay. Now, I do have like one example for a combinational circuit that might actually be interesting to verify. And so here, this is a gray code circuit. Let me try to make this a little bit bigger. So what is gray code used for? Gray code a lot of times is used for crossing from one clock domain to another if you need a counter. And so now I'm not a physical design person, so I cannot tell you all the physics that goes on when you're crossing from one clock domain into another. But basically, one of the design principles that you have to follow as a digital designer is that you should never have more than one bit flip at the same time, because if you flip multiple bits, they might, the other side might see them at different times. So actually, like, causality might be inverted in some sense. And so basically, you need to only ever flip one bit at a time. And now if you have a counter, if you think about it, if you're counting up in binary, actually multiple bits flip, right? If you go from 3 to 4, then you have 3 bits that flip. Like the bits 0 and 1 go from 1 to 0, and bit 2 goes from 0 to 1. And so that would not be good. Now, gray code is basically a way to represent binary values such that if you increment, only ever one bit will flip. Okay. And the other nice property is that it's you can convert from binary to gray code and from gray code back to binary, and you will always get the correct result. So there's no loss of data here. So that's the first basically invariant that we want to encode, is saying that if we have an input value and we convert it from binary to gray code and then back from gray code to binary, then the input should always be equal to the output, meaning, right, there's no input value for which we lose information. And so here we can do a check. You see this property is actually like parameterized because Chisel is a generator language. This is basically a Chisel module, just one that has an assertion in it. And so we can parameterize it on the width of this gray code, and we can actually like run this check for different widths of gray codes if we wanted to. I did choose like 64 here, because 64 is like it's a big value, and so meaning that we couldn't just write a test that tries out all possible inputs, because if you think about it again, we would need to try out 2 to the 64 different inputs to be sure that there isn't an input which violates this property. Now, this is pretty boring here because the property actually holds, so you don't actually get like any error message or anything interesting. So we could always like say something like, okay, input is not equal to output, which of course won't hold. And then we could get something where it says like, oh, if I have a 0, it becomes 0 in gray code, and then it becomes 0 again in the output, and that's actually the same. So so here you see the property is violated. I fix it again, and it all works. Okay. Now, the more interesting thing about gray code is what we said is that only ever one bit flips when incrementing. So now how can we encode this property? Well, so here's the solution, basically. We take A to be some input, and then we say B is just that input plus 1. So we're incrementing by 1, right? We just have a counter, we increment by 1. Now we convert both A and B to gray code, and then we check how many bits flipped. And so how do you check how many bits flipped? You basically calculate the Hamming distance. And so this is a way to calculate the Hamming distance. There's this pop count function in Chisel, and you just take the XOR of these two values. If you're not familiar with Hamming distance, try to read it up at some point. It basically just says how many bits flip between these two values. And now we're saying, okay, this Hamming distance always has to be 1, because we only ever want to have 1 bit flipping between converting from between two binary values that are just one is the increment of the other. And so now we can run the same thing again, run it again for 64 bits, and it doesn't. It's always correct. Now we could mess up this whole thing. We could say, okay, B is A plus 2, then of course it probably doesn't hold, and we'll get a counterexample. We'll say like, okay, there are these two values, which are the gray codes of these inputs, but their Hamming distance is actually 2. Okay. Which makes sense, right? If you like increment by 2, then there would be 2-bit flips. You can turn this back to 1, and then the property holds, no problem. Okay, so to recap, if we want to verify our combinatorial circuit, we need to write an assertion that defines a property we want to check. So if you don't have an assert, the solver or the verify command is always going to say, yes, everything is great, because there's nothing to verify. This SMT solver actually helps us prove, and this is something that I haven't really gotten into yet, but it actually helps us prove for all possible inputs that the assertion cannot be violated. Remember that if we get unset, that means there's no assignment such that the property can be violated. And with the Chisel interface, if you have a combinatorial circuit, just say bounded check 1, and it will give you a full proof, meaning there's no possible input that could violate the property. Why that's important, or why it will ever be different, we will see when we get to the next chapter about stateful circuits. But for now, this might be a good time to pause if there are any questions.
Any questions? Okay, I think everybody's on board. This is great.
All right, cool. So yeah, now we're going to talk about sequential circuits. So these are circuits that do have state. They have some register or some memory. And so here is a sequential circuit called my counter. What does it do? It has some input called enable. It has a register called count. It's just 32-bit wide, just so that we don't have to worry about overflow so much. And what does it do? It says, okay, if it's enable and the count is equal to 22, it will go to 0. If it's enable and the count is not equal to 22, it will increment the count. So basically, it should be a counter that counts up to 22 and then counts back from 0. And here we're asserting that the count never reaches 10. Now the question is like, can it reach 10? It should be able to, right? So now we can say, okay, verify my new counter. And for now, let's say like, okay, bounded check 1, and see if the assertion can ever be violated. And we see there's no error message. So I guess this assertion always holds. But that should be true, right? Like you kind of expect this counter to be able to reach 10. You just enable it for 10 cycles, and then it should reach 10 because this whole overflow check only happens at 22. Well, so the problem here is we actually did the bounded check for 1, but we need to actually execute the counter for like 10 cycles to reach this bad state, or this assertion violation. So let's try to actually like give it 10 cycles. Oh wow, now we actually reached this assertion violation. And you can see here you're actually given a trace. This trace is just comes from this printf here. So we have this printf that prints out values. And that's one of the nice things also about the formal verification integration with Chisel test, is that you can actually use printfs, and it will basically, once it finds an example of how the property can be violated, it will replay the circuit with all your printfs enabled, and so you'll actually be able to see all the values printed out. But so in this case, we can see, okay, we just enable all the time, and at some point count reaches 10. And that makes a lot of sense here, right? Now we could change the circuit to like only go up to 9, right? Something like that. And now if we run this, it will actually not find any assertion violation because we cannot ever get to 10, right? Now I can change it back, and if we run it, it will find the same violation. I can change this count to 20, and it will not actually find a bug just because we only set the limit here to 10. If we actually send it to like 25 or something like that, then it will find the violation. It just won't fit on my slide. Okay, so this is just a counter, and we've just been playing around a little bit with this assertion, with when it overflows, and also with this verify command and the bound, right? So you get the notion that somehow this bound is important if you are verifying things that have state. And the reason for that is because the state evolves over time. So we're looking at multiple cycles, not just one cycle. And that's like the key difference between the combinatorial and the sequential circuits is that for the combinatorial circuits, all properties can be reasoned about within only a single cycle. For a sequential circuit, you might have to look at like an arbitrary amount of cycles potentially. Now, how do we reason about these sequential circuits? Because I showed you the Chisel circuit, but the Chisel circuit is not an SMT formula, and it's not like directly straightforward how you would even derive an SMT formula. So one of the things that basically all formula verification tools do is they kind of abstract these circuits into what's called a transition system. Transition system essentially is kind of a state machine that has some states and some transitions that describe how to go from one state to another. So now let's try to define a transition system for our counter from the previous slide. So here's just like a small example of how the state could evolve. And you see, here's basically like the example state. This whole enable thing, you would say, oh, it is actually like an input, right? But you can also treat it as a state, and we'll see in a minute why. But basically, we could say, okay, in S0, count is 0, enable is 0. That means in S1, the count will still be 0 because we know when enable is 0, the counter doesn't count up. And let's maybe say like enable is actually 1 then. And that means that in the next state, count will be 1, and enable could be something new and arbitrary, right? Now, what is the goal of verifying this circuit? Well, the goal is to reach a state in which an assertion is violated. And in our case, an assertion is violated if the count reaches 10. So we could say, okay, there's this error state where count is equal to 10. And we just kind of have to think about, is there a way to reach this error state? If we're sure that there's no way to reach this error state, then we know that the assertion can never be violated. If we can find a way to reach this error state, we can actually show all the states and the evolution of those states and say, okay, if you get these inputs, then you will get to this assertion violation. Now, over the next couple of slides, I want to try to basically implement our own model checking, meaning like our own verification algorithm to try to verify this particular circuit. So we're trying to do the thing that Chisel test does under the hood that we looked at in the previous slide, but we try to do it only for this one particular system, not for any circuit, but just for this one particular circuit. Now, what do we need to define? We need to define some sort of state. So here we have a state that's just a counter and an enable. We have a function to make a new state. So the new state will basically just contain two symbols. So symbol is just like a variable, essentially. And one is the counter value, and the other one is the enable value. We have I, which is a predicate that says that is true when we're in the initial state. So basically what this does is it just constrains the counter to start at 0. So we're saying like, okay, if this is the initial state, then that means the counter value is 0. You see that there's no constraint on the enable, and the reason for that is that the enable is an input, so it's always unconstrained. It can always be freely chosen every step. The other predicate that we're encoding is this T, which is called a transition relation. And what that does is it basically says like, oh, what has to be true about two states such that one state follows the other? And so here we're basically encoding that. And what do we need? Well, so here we're basically saying like the next counter state is, so basically we're making an SMT formula that tells us whether what the next value of the counter should be. So we're basically translating from the previous slide this code, this Chisel code, into an SMT formula. And so how does that work? Well, we say, okay, ITE is basically a mux. So basically we're doing a case split. We're looking at different cases. We're saying, okay, if the counter value in the current state is equal to 22, then the next value, if it's enabled and the counter value is equal to 22, then the next value will be 0. If it's enabled and the counter value is, if it's enabled and the counter value is not equal to 22, then we add 1 to the counter. If it's not enabled, then we just use the old counter. So this is how we can determine the new counter value from the old counter value and the enable value. And now we're saying, okay, if S1 is actually a state that follows S0, then that means that the counter value in that state is equal to the counter value that we derived from the previous state. Okay. Now there's one more predicate that we need, which is called P, and P is describing basically the bad state. So the bad state is when, it's describing whether the property holds, so whether we're in a good state. And so basically we're just inverting the thing that we're looking for. We're looking for a state where count is equal to 10. And we're saying like, okay, the count is not equal to 10. So that means we're in a good state. Now we can create like 2 states here, which, just creates these symbols. Now, what do we do with all of this? Well, I guess, okay. What do we do with all of this? But also like the first question here is, what happened to our clock and reset values? Because, in Chisel, we do have like a count that gets reset to 0. And there's like a reset pin that controls that. There's also a clock that will advance the register. And the answer is that when we went to the transition system, we actually kind of like hand waved away the clock and reset. So this conversion here that we're doing, it assumes that your circuit has only a single reset pin and only a single clock, which is normally true, or which is true for a lot of circuits, and enough circuits that this handles a lot of cases. There are special things you can do if you have multiple clocks or if you have multiple resets. But for now, what we basically did is we assumed that the system always starts in the reset state. So that's why we basically made this constraint to the counter is 0. So we're kind of ignoring the reset pin, but we're saying like, oh, the reset pin just sets this counter register to 0. So let's just say initially we start at 0 in this transition system. And the clock, we're basically saying like, oh, any like clock tick represents a step in this transition system. That's kind of what happened to our clock and our reset. Now, with these predicates that we defined, the initial state predicate, the next state predicate, and the assertion, we can then try to do bounded model checking. What does bounded model checking mean? Well, so we saw earlier that if we have a combinatorial circuit, we can turn that whole circuit into an SMT formula, and the SMT solver will tell us whether it's satisfiable or unsatisfiable, whether a bad input exists or not. For a system that evolves, we can't easily do that because we don't know how many cycles it's going to execute. So the next best thing we can do is we can just start and assume like, oh, maybe we can reach the bug after 1 cycle. So we just encode the system for 1 cycle. And then we'll encode it for 2 cycles, and we'll encode it for 3 cycles, and so on. That's what's called bounded model checking, because we check up to n or up to k cycles, basically. Now, how do we do that? Well, we start with the initial state. We say, okay, assume there's a state 0, which is an initial state, and then check that the assertion is not violated. And then we say, okay, if that's true, then say there's an initial state S0 and the state S1, which follows S0, check if the assertion can be violated in state 1. And so if you look at this, right, we know that our counter does not exhibit any bad behavior for the first 9 cycles. So of course, we won't get to a bad state in this case. Now, for the next state, we can just say, okay, make another state. And now we're saying, okay, we have this initial state. We have this state that follows S1, which follows S0. We have S2 that follows S1. And now can we reach the bad state, right? And so the interesting thing here is, right, this is kind of like each one of these states is symbolic. So it is encompassing any possible state that you can reach in 1 or 2 cycles, right? So it is pretty powerful, but it is still constrained. If there is no, if you need to like, take 3 steps in order to get to this bug, then this will not find it because we're only looking at 2 steps. And yeah, here we won't find anything. So instead of like continuing and making new states manually and everything here, I actually wrote a small routine here that does bounded model checking for this particular circuit. So the thing that we're doing here, the reason why this is kind of small enough to fit on a slide is because we encoded these predicates like I, T, and P for one particular circuit. The hard part that makes like the actual like implementation for Chisel test much more complex is that it actually works for any Chisel circuit. So for any Chisel circuit, we basically had to write a compiler pass that then derives all of these conditions in order to check them. But here we hard-coded the conditions, so that makes things a lot easier. And now we have this BMC routine. What does it do? It like starts with a state 0, and it keeps a list of all the conditions that we're looking at. And so basically just says like, okay, state 0 is the initial state. And now we go from 0 to k, so we're doing up to k cycles that we're looking at. And then in each cycle, we check whether, given our current list of conditions, the previous state can reach an assertion failure. If that is true, then we should print out, oh, bug found, and we return. Otherwise, we create a new state. We add to the conditions that this state follows the previous state, and we make that new state the new previous state. And that way, it will basically keep on doing the thing that we were doing manually earlier. So here we're like basically adding things here and like checking for each state whether we can reach a assertion failure, and we're just doing that automatically here now. So we can do a BMC for 5 cycles, and we won't find anything because we know that the counter only goes bad after 10 cycles. So now we can up it to 10 cycles, run it, and it will actually say, oh yeah, we found a bug, and it will try to print out some counter examples, but it's not as nice as the actual Chisel implementation because we're doing this in just a couple lines of code. But so this might be something that's useful for you to run at home because, it is actually implementing bounded model checking for one particular circuit, not for all circuits in general, but for one particular circuit, it is the full implementation of bounded model checking. Now here is like a visualization that might help some people. So in this case, we're actually saying the bad state is the counter is equal to 500. We're just doing 10 earlier, but 500 or 10, same thing. But so the way you can think about it is there is like this state, right, that you're in. At some point the counter is 0, and you want to know, can a counter ever become 500? Now, one thing we can tell about the counter is there are only like 2 to the 32 different values that it could take on because it is a 32-bit variable. So there is this finite space, which is represented by this green box, that contains all possible values of counter. And now, if we're doing bounded model checking, we're basically looking at all possible states after one step. And so we know after one step, the counter is either 0 or 1, depending on whether the enable was true or not. After 2 steps, the counter is either 0, 1, or 2, depending on when the enable was on. And so basically, bounded model checking is like sort of slowly expanding the state space, and trying to see see if any of the state space that we can reach overlaps with this bad state. And like in this case, because the counter can only ever increment by 1 at a time, if we wanted to get to 500, we'd have to do 500 steps, basically. So what does this teach us? It basically teaches us that bounded model checking is pretty powerful, assuming that there is a way to quickly get to your bug, like meaning like a few enough cycles. But you could always come up with an example where you just need so many cycles that it's infeasible to go that many cycles. Because the other thing to note, and I don't really have a good demonstration of that here, but one thing to keep in mind is that the more cycles you do, the slower it gets, and it gets like a lot slower. It doesn't just get linearly slower, it normally gets like exponentially slower. So if you like start saying like, oh, I want to look at the circuit and make sure that it doesn't have a bug after 1,000 cycles, it probably won't ever finish with the bounded model checking unless the circuit is super simple. So that's something to keep in mind. Now that's the basic explanation of bounded model checking. Are there any questions at that point?
Yes.
Yeah.
I have a question. Can you apply infinite steps in Chisel? Unbounded model unbounded model checking.
No, not at the moment. So basically, there's ways to like prove things about your system such that they hold for unbounded number of steps, but then you normally sacrifice this nice property here that. So in this case here, if your verification fails, it will always give you an example of why it fails. There are ways to try to prove things for any number of steps, but then if it fails, it might just be because some assertions aren't strong enough, and you will probably not get a real counterexamples that demonstrates you where the bug is. So this bounded model checking is very useful for like bug finding, but yeah, it doesn't give you a full proof. If you have time at the end, there are some bonus slides about k-induction, which is not implemented in Chisel right now, but k-induction, you can use that to prove that no matter how many steps you execute, your counter can never reach 500. Does that answer your
Thank you.
question?
Yeah. We can discuss at the end. Thank you.
Cool. So we do have an application example here. So this is a queue from, I think, an old queue lecture. And this is just like an implementation of this queue. Now let's see if this example will work. Okay, so we have the queue, and we want to write a property about it. And so one thing that I feel like makes formal verification always hard is, well, for one, it's just kind of a little bit niche, as I mentioned earlier, because it is sometimes hard to get your hands on a tool that can actually do formal verification for you. The other thing is that it is sometimes really hard to find the right thing to express. So there are certain things that, you have like a lot of experience with testing and writing tests, and you kind of know like how to write your tests so that you can catch a lot of bugs. But with formal verification, sometimes it's really hard to know just what kind of property to specify such that it will be, it will be like useful for finding bugs. And I think the answer to this is just that you need like some experience with formal verification. You will get better and better at sort of finding the right property. And so I want to show you like an interesting property that I actually like learned from someone else's code, which is this data integrity property for queues. And the basic idea here is just that when data goes into a queue, it should exit again at some point, and it should be in the correct order. So, if you put 1, 2, 3 into a queue, it should come out as 1, 2, 3 and not as 3, 2, 1 or something like that. So there shouldn't be any reordering within the queue, and you should eventually get the value back out of the queue. Now, how can we express this in Chisel? Because as you might have noticed, like all these properties that we're expressing for formal verification have to be actual like real Chisel circuits. That's like one of the other differences between testing and this. Like in testing, you can just write your Scala code for these properties in order for them to be analyzable and like for us to be able to discharge them to the SMT solver. They need to actually be Chisel circuits with these added assertions. And so what we do here is we basically make a module that encapsulates a queue. It has a new input for the queue, and it just hooks that input up directly to the queue. So basically just like has a queue inside and just like exposes all the inputs. And then in addition to that, it like counts how many elements are in the queue. And it has some facilities of printing what happens with the queue. And so this is kind of interesting to us because we are going to look at a queue, we're going to try to find a bug, and if we find a bug, we need to get some counter examples. So I just want to demonstrate to you right now how this works. Well, right now it doesn't do anything, but we have the special fail after, and you can look into the code to see how it's implemented. But essentially what it does, it will just like include a counter and an assertion that makes the verification fail after 3 cycles. And this means that then we can see what the output is of this trace that we made here. And so you see, basically, it will print out the cycle that we're in. So this comes from here. And then it will print sort of what is the element count in the queue from 0 to 0, 0 to 1, 1 to 2, 2 to 3. And it will print what happens with the queue. So here we're seeing like, oh, 0 gets in queued, 0 gets in queued, 0 gets in queued. And that's why like the element count is going up. Okay, so this is just for you to understand sort of this trace capability, because we're going to use that in order to study the property that we're trying to write. Now, this is the first attempt at writing a property. And we're trying to basically trying to say that, the first element that goes into the queue, we want to make sure it comes out correctly. So what do we need to do for that? Well, we basically extend our queue trace to like add this property, and we need some registers to trace to keep some information for our property. The first one is we want to see whether there is a package that we're tracking. Did something go into the queue already that we're tracking? And if we're tracking something, then we want to have the packet value so that we can later check when it comes back out of the queue. We want to check that the value is the same thing that went into the queue. So how can we then use these? Well, let's say we're not actively tracking something and the enqueue of the queue fires. So something was enqueued and is being enqueued. Then we go into active mode and we remember the packet value, and we're just printing out, oh, we're tracking this value now. If we are tracking a value and something comes out of the queue, then we say, okay, we're done tracking. And now let's check to make sure that whatever came out of the queue is what entered the queue initially. And now we can verify our queue with that. But what happens? Well, what happens is we actually get an error. Now the question is like, why do we get an error? What is happening here? Okay, so we look at our trace. We see something goes into the queue. A 1 goes into the queue. Then 128 goes into the queue, 1 comes out of the queue. Then 0 goes into the queue, and then another 0 goes in, and 128 comes out. And then we're saying, oh, but 128 is not equal to 0. So what is going on here? Well, we see there's this tracking thing, right? So initially we see the 1, and we're saying, okay, we're tracking the 1 now. That's great, because now the 1 comes out in the next cycle, and we're saying, okay, this is great. A 1 came out, and the property holds. But now what happens is we also like include 128 in here, but we didn't write it down because we're still tracking something. But now a 0 enters the queue, and now we're like, okay, let's track the 0. But then the next time we're getting something out of the queue, of course 128 comes up because that was included here. And now we're saying, oh, but we expected a 0. So that's a problem, right? But this doesn't seem to be a problem with the queue. This seems to be a problem with our property, because we are only tracking one thing at a time, and we don't notice if there's something else sneaking into the queue. And so that's a bit of a problem. How can we work around this? Well, so this is our second attempt. And it basically adds this new thing, which is the packet count. What does the packet count do? Well, now if something enters the queue, we will actually remember what the number of elements in the queue was at that time. And now if something comes out of the queue, we'll actually start counting. We'll say, okay, if this basically we'll decrement this counter, and only if the counter reaches 1 will we check the element. So now we can look at this, and you'll see that there's like another thing it complains about, but at least we seem to be like not having the same problem as last time. So now let's look at the trace that we're getting and see what's going on. So we see a 64 is entering the queue, and we're tracking it. Then it comes out of the queue, and it's okay. Now a 9 exits the queue, and then a 0 goes into the queue, and we're starting to track it. And then like there's a bunch of other things going into the queue, and at some point we're saying like, oh, the thing that came out is not what we wanted it to be. And the reason why like so many things have to come out of the queue is just because we're tracking at 3 elements, and then it takes a while to like dequeue that. But now you might be saying, oh, this is kind of weird, right? Why are we at 3 elements here? And that's actually the problem that we're seeing here, which is that something enters the queue, something exits the queue, even though the queue should be empty here. So we're getting a 9 out of the queue, and then the count goes from 0 to 3 because it underflows. And that is actually a real bug that was in this queue when I first made these lecture slides. Now the big question is whether I remember how to fix it. And the nice thing is that I do have this in here where I can just fix it magically. So what happened here is the way that the maybe full was assigned was not correct. And this is actually a very tricky thing to find. So I did start with these queues, and I already had a property written down because I was using it for some other queues. But so then I basically ran my existing property on all the queues for this lecture or for this class, and I found one where there was a problem. But then even after finding that and getting a similar trace to what you saw just now, it took me another hour or so to actually find out what was going on. And the way that I found it was just by comparing the logic for the maybe full to some other existing queue that I had access to. And I found that there is like another there basically you should like calculate like this and not like this. Now, the formal stuff helped me find this bug, and this queue had been used in a run of this class, and people hadn't found this bug. So I feel like this demonstrates a little bit how useful it can be. But of course, it didn't quite point me directly to where I should look to fix it. But other methods helped, namely like comparing this to an existing working implementation of a queue. But now that we fixed this, we can like rerun our code. And I should probably comment this one out. This one is still going to fail because our property is bad, but now we can rerun this one, and we'll see what happens. This is taking a little while now. Okay, so now it basically doesn't find any assertion violation within the first 10 cycles. So that's great. So that means we did fix our queue, and it seems to be working. There is one small thing that we can add to this tracker, which is currently the problem is basically while it's tracking a packet, it cannot track another packet. It can only track one packet at a time, and it will always deterministically track the first one it sees and then the next one it sees. But there is a way to give the solver a little bit more freedom, meaning that we can add this enable pin, and then we can say, okay, we only start tracking if we're not active and also the enable is true. And what this means is basically if there is a bug that that only turns up if you track the second packet instead of the first one, then the solver can automatically decide to do that, and that means you might potentially be able to find the bug in fewer cycles. So if we run this, it's kind of boring because we just fixed the queue. So we'll just end up saying like, oh, there's nothing wrong with it. But just for completeness sake, this is kind of like what a full property should look like with these like this enable that basically allows you to like pick any packet instead of picking like always the first one. But yeah, that is basically the queue example. Yep.
Can we go back one slide? So this is really interesting, this notion of you track only one packet and then you give it the freedom to choose which packet to try to get more coverage. And so, you know, a naive alternative might be to try to track all packets. Is that making the state space too much bigger? Is this way more efficient? Is that why you did it this way, or?
It's slightly worse. I do actually have, if you look at my thesis, there's actually a chapter where I am actually looking at queues, and I do both. So like the advanced. So the thing here is like this enable thing basically adds a sort of like if you wanted to like actually use this checker with random testing, you would actually then have to randomize the enable, and it kind of gets a little hairy. There is a version where you can just track everything, and that's easier if you want to combine it with random testing. And so my thesis actually has a graph where it shows this like this property expressed like this way, and then also the way where we basically just instantiate a known good queue and then just compare the inputs and outputs. And it is like slightly faster to do this version here. But yeah, you could also do it the other way. Basically, you just instantiate a Chisel queue, and every time something goes into the queue that you're checking, you also put it into a Chisel queue. And every time something comes out, you also dequeue from a Chisel queue and just make sure the value is the same. That also works.
Cool, great. Other questions?
Awesome.
No, okay, please continue.
All right, so this is the end of the main part of the lecture. So to summarize, formula verification can exhaustively verify a circuit, which is kind of cool. So for a combinational circuit, you can basically prove things about it. If you want to use it with Chisel, you need to write your checker in Chisel. So your property needs to be written as a Chisel circuit with an assert. It is not software like normal Chisel tests. It's not Scala, it's really all in Chisel. One thing that's kind of neat is that sometimes a checker can actually be smaller than a test if you find a good property to check, but it can be really hard to figure out what is a good property to check. It can find interesting corner case bugs, so this queue bug, for example, of course, like it's not as well tested as like a real queue would be, but like, people were using it, or like, it was in the lecture, and like a lot of people looked at it, but this property found very quickly that there is a corner case bug in it. Here are some links. I hope they still work. There are some examples here for formula verification. You can send me an email. This is I think has my Berkeley email, but you can also find my Cornell email if you want to email me. This is the Chisel test library. Unfortunately, it's no longer being developed just because a lot of the Chisel ecosystem moved on to a different infrastructure, and there's no one there to spend a lot of time porting Chisel tests to the new infrastructure. And there's a Chisel community chat if you want to get involved in the community. So I do have a couple of bonus slides. I don't actually know how long the lecture is, and also I want to give people the opportunity to ask questions first. But if there aren't any questions, then I would go to bonus slides. I just need to know how many minutes I have.
Sure. Well, first, let's thank you for the main talk. This was fantastic. So yeah, we actually do have time. So I don't know if you noticed this quarter, I'm teaching Tuesday, Thursday rather than Monday, Wednesday, Friday. So it's a 95-minute slot. So there's definitely time, but maybe I'll be quiet and see if there's any questions from the audience first.
Yeah, let's do questions.
Yes.
Is there any room to, I guess, kind of reconfigure this so that do something like synthesis, going from specifying some properties about a circuit that you want to have, and then from there I guess like reorienting the problem?
Yeah, that's a really cool question. We actually kind of had a synthesis example in here. If I go back all the way, it's a very boring synthesis example, but this was kind of a synthesis example here, where we're solving this question here. And so you could kind of express that with Chisel, but it's not built in. So I guess like the important difference here is like here we're asking. So normally what we ask with this solver is basically we like ask, does there exist an A such that, right? That's what we're asking. Now synthesis will actually ask, does there exist an A such that for all C, blah, 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 right? And I actually cheated here a little bit because I chose a fixed C. I said, okay, C is just 145. But in reality, our synthesis actually does ask, like, is there an A such that for all C, this rewrite is correct? And so if you actually wanted to do that, you'd have to, you basically are stuck with the problem that your solver can only do existential queries. And so what you could do is you could basically do what I did here, saying like, okay, we just pick some C, like 145, and we get an A. And so in this case, you would get the A being 2. And so now you can ask a different question. You can say, okay, is there a C for which this doesn't work, right? Like, so you could say, okay, is there a C such that this is not equivalent? So I would have to create. The problem is I don't actually have like a C here, but I will just reuse A. So we'll use A in place of C now, and we basically will have this left shift off A by, and now we use the A that we found as the literal. Let's see if this works. Yeah. Oops. Oh yeah, and we need to invert this because we're looking for a C for which this rewrite is not valid. And so in this case, we'll say unset, so that means you're done with your synthesis. But it could be that the A that you chose is actually like only works for the special case of C being 145, and you would get a different C, and then you would say, oh, is there actually an A that works for both C's? And so this way you actually get into a CGIS loop, which is one of the ways that you can do synthesis. But yeah, none of this is actually implemented in Chisel test, so you would have to kind of do that yourself. But yeah, you can kind of like you could in theory like implement synthesis using very similar ideas to this, just that you then have to basically do this iteration between like exists between these two different kinds of queries, because you have like an exists for all query, not just an exists query. Does that answer the question?
Yeah.
Great. I guess relatedly, I assume there's some sort of way to specify constraints or properties on inputs.
Oh yeah. If you want to like sort of constrain the inputs that are viable, you can use assume, which works basically like assert, just that it will prevent the solver from considering any inputs that violate the assumption. So you could say like, oh, assume this input is greater than 1, and then it won't consider 0.
Like for example, for your overflow example, you could say, assume that input is less than, that max value.
Oh, yeah. Let's actually try that. Of course, I don't know what the max value is, but oh no, actually we do have it here.
Copy it, right?
The question becomes, how do you actually spell that in Chisel? Well, let's just say like we know that when the overflow occurs, B will be 0, so we'll just say B is not equal to 0. That's much easier to write down. And now let's see, and it passes. Okay, so we restricted B to not be 0. We can restrict B to not be 1, and then it will still find the counterexample. Okay, and here we actually just we constrain something that is actually derived from the input, but you can also do that. That's no problem. Okay.
Great. Do we have other questions from the room?
Yes. So suppose you run bounding model checking for a very large number of cycles, like 10,000, 100,000 time cycles, and you can't find any violation. So, and that means the property is asserted. Is that right? And
No. So there are like ways to determine a bound at which you have a full proof. but they are not that easy. So there are like some ways that you can check that that you explored essentially the whole state space that you can reach, but in reality they don't really work super well. But yeah, if you just give it an arbitrary circuit and you tell me I ran bounded model checking for 100,000 cycles, it doesn't mean anything in terms of guarantees. But one thing we do observe a lot of times is that a lot of bugs can be triggered pretty quickly. Okay, so basically, there are no guarantees if with bounded model checking, but there is this experience that a lot of times you will actually find a lot of interesting things.
And so in Chisel, if we write Chisel, what kind of tools can we use, like say Jasper or Yosys for the formal verification?
Well, so there is this part of Chisel test that you can use to do bounded model checking.
Okay.
Right?
Yeah.
But of course, if you generate Verilog from your Chisel, you can use any of the Verilog tools as well.
It supports. I see there is a Z3 prover. So does Chisel test support theorem prover?
Chisel test basically just supports like bounded model checking essentially. It doesn't support like unbounded proofs.
Okay, and the problem of the Q, verifying the Q, can we use uninterpreted functions to verify that? Like you can verify the order of the memory read or write. So I think that's similar to the Q operations.
So you don't really need uninterpreted functions for this. Because the queue is using a memory in Chisel, it will actually be translated into the theory of arrays, which is somewhat similar to the theory of uninterpreted functions, but not 100%. But all of that will basically be done in the background for you. You don't need to do anything specific there. Uninterpreted functions in hardware verification, the place where they are used sometimes explicitly, like where you actually kind of do it intentionally, is because SMT solvers are really bad at reasoning about a lot of data path circuits. So for example, if you were going to ask an SMT solver whether let's say you have like a gate level optimized multiplier, and you want to ask an SMT solver whether that one is equivalent to just writing the multiplication in Chisel, there's a good chance it will just never give you an answer, just because that ends up being a really hard satisfiability problem, and it just won't be able to solve it automatically in a reasonable amount of time, assuming that multiplier is larger than like 8-bit or something like that, right? For smaller things, it can still give you an answer, but if you have like a 64-bit multiplier and you ask an SMT solver, is this gate level version equivalent to just the high level multiplication, it will never give you an answer. And so sometimes what people do is they say, okay, I know this particular component implements multiplication, but I want to know whether the control logic is correct. And so then they might actually replace this low-level multiplier implementation with just an uninterpreted function. And in the specification, just say like, oh, this uninterpreted function has to be applied to the inputs. And then you can basically like separate verifying the data path from verifying the control logic. And so that's where uninterpreted functions can be very useful.
Okay, thank you.
Yeah.
Great. I think there is time for a couple of bonus slides, if you would like.
Yeah. How long are we going? Just to the.
I mean, we obviously have a hard stop for the room in, I guess, 20 minutes, but I think, no need to do everything, right? If you everything feels natural to you.
Yeah. No, I think last time we did the slides in like 15 minutes, so I think this should be fine. Okay, so the thing I want to talk about in the bonus slides, first thing actually is not proving things, but it's temporal assertions, which I feel like are little less in the weeds than the whole proving stuff. So what are temporal assertions? Well, right now, all the assertions we wrote were about a particular input or a particular state in one particular cycle. Now, of course, our Q property was kind of talking about multiple cycles because we're talking about enqueuing something and later dequeuing something. So we kind of already wrote an assertion that spans multiple cycles, but we kind of wrote it manually using just Chisel hardware to basically keep track of everything. Now, in hardware designs, there are a lot of things where we have to sort of reason about multiple cycles at once. And so normally there is some library support or some language support that allows you to express properties that talk about not just one cycle, but about multiple cycles. And so an example of like a, like an English language specification that is temporal is this little snippet of the AXI4 specification. So AXI4 is like this interconnect protocol, and it's specified basically by ARM or like some ARM related consortium, and they have these ready valid interfaces, and they add some restrictions to them. And so the restriction here is that basically after the valid signal is asserted, the information has to be kept stable until we get ready and the transaction actually happens. So basically for ready valid interface, the transaction happens when valid and ready are true in the same cycle. And here, basically, what this property is saying is like when you start saying that your information is valid, you cannot just go ahead and change it. You have to keep it the same until the transaction occurs. And so now I want to use this construct we have in Chisel test called past to implement this property. And what does past do? Well, the easiest way to think about it is the past will basically just access the value of the signal in the previous cycle. It will do some other things because like there's a certain problem where like if you're verifying things in the first cycle of your check, there's no previous cycle, and so it'll actually delay your assertions by one cycle. But that's an implementation detail. The important part here is that it allows us to like somewhat more easily. It allows us to express this property without having to resort to creating our own registers or creating our own Chisel logic. And so what we can write here is we can say, okay, in the previous cycle, valid was true, but ready was false. So that's kind of this situation here. Valid is true, ready is false. Then that means valid should still be true because you cannot deassert valid without a transaction happening. So this is another restriction I didn't mention earlier. Basically, once you say valid is true, you can't just say no, now it's not true unless a transaction actually has happened. And then we're also saying that the bits should be stable. And so stable actually uses past in the background to say, okay, the previous value of the information should be the same as the current value. And the bits shouldn't change. And so this is basically then this property that we implemented here. And the Chisel test library in the background will actually automatically turn all of this into Chisel circuitry that can then be converted with the usual compiler to a format that the SMT solver can then understand. But it's not only good for the SMT solver, it can also be these assertions with past and stable and things like that can also be used in testing. So this example that I have here is actually with testing. So we're actually like we're basically instantiating this check. So we're not actually instantiating any AXI hardware. We're just instantiating the property that we wrote, and then we just use a standard like Chisel test to basically drive this hardware. So initially we say, okay, valid is true. This is the information. Ready is false. We take a step. Then we say, okay, ready is true, meaning a transaction happens. And so now we can change the value. And then we say, okay, but now ready is false, so we don't have a transaction. But then we're not allowed to like change the value again because because basically valid will still be true. So I can run this, and we'll actually see something will change. Something will go bad. What does it say? It says valid may not be deasserted without a ready. And so this is what's happening here. We're basically saying, okay, valid is false, but there's no ready that we're setting. So if I disable this thing, then now it all works. But here's the second part of the property where basically we cannot change the information unless there is a ready. So we change information here, and then they're like, oh, you're not allowed to change it. Now, if we actually leave the ready true here, then we are allowed to change it. And you see that that's all fine. Also, if we leave the ready true, then we are also allowed to like revoke the valid because the transaction happens basically every cycle because the ready is true. And so here you can see basically play around with it a little bit at home. You can see how these temporal assertions work and how they are also useful for tests. So like that's one of the nice things about writing all these assertions in Chisel. A lot of them actually can also work for just normal tests. You just then have to like decide the inputs yourself, and you cannot just rely on the solver to find the inputs for you. Yeah, and so here, this is for you to look at home. So System Verilog and VHDL, those like standard industry languages, they have a much richer language for complicated temporal assertions. And so here are a couple of examples you can look at, like some open source code that shows you some more complicated temporal assertions. And that's on temporal assertions. Are there any questions about temporal assertions?
Getting positive nods, ready to go on.
Okay, cool. So now we're getting to this part that we've alluded to earlier, where we are trying to reason about more than just case steps. We're trying to reason about all possible steps that the circuit could take. And so in this case, we're actually kind of using the same counters system and the same stuff that we did for the bounded model checking example, just that now we actually say the bad state is reaching 500, because the counter only counts up to 22, and so that means we can never reach 500. So this K-induction technique, we're basically trying to prove a property to be true, but if the property is not false, it is not actually true, it doesn't actually help us so much. So like BMC, bounded model checking, is good for finding bugs, and only if you have some confidence that your assertion actually always holds, would I recommend that you try to prove it. Because if your proof fails, there's always two options. It could be that your proof just isn't strong enough, or it could be that the property is actually not true. So always try to first do like some testing or some bounded model checking before you go to proving your property. And so now this is a property that we are pretty certain will hold, so we can try to prove it. Now, if we go back to bounded model checking, right, and we're thinking about this property, the problem was that we have this state space, which we know because the counters are 32-bit counters, so we only have 2 to the 32 different states, which is a lot of states, right? And we know that every time we take a step in our bounded model checking, we actually only advance by 1. And so getting to 500 would require a bound of like 500, which is really high. However, with K-induction, we don't have to, we don't necessarily have to do that. We can basically define a different state space. We can basically define like a state space that might be an over approximation of the actual reachable state space, and then use that to prove the property. So how does that work? Well, let's say that that basically we say that the counter can only ever be in the space where it's not equal to 500, right? Like we say, so basically we're trying to and we're trying to prove that basically for the base case, which is the same thing that we've done before. But now instead of saying, okay, we have this state which is the initial state, and then we have another state, and then let's check whether the property holds in that other state. We say, okay, we are assuming we start from a state where the property holds, and then we have a next state, and then the property shouldn't hold. So we're saying, like, is there a way to get from a state where the property does holds to a state where the property doesn't hold? And the problem is that there is, right? So you could say, oh, the counter is 499, and then if we increment, it goes to 500. So maybe we can actually get to 500. We don't really know, right? But this is basically why I'm saying, like, if you get a failure in K-induction, you don't always know if it's actually because your circuit is wrong or because your proof just isn't good enough. But now we actually know that we cannot get to 500, right? Basically, what is happening is that we know that we basically know that the counter can never be greater than 22. So what we could say is we could say, okay, the counter can only ever be within the circle that is smaller than 22. And then we basically have to show that every step from a particular point in the circle will land in the circle. And you can think about it for a counter that it makes a lot of sense, because from a counter we can go from 0 to 1 to 2 to 3 to 4 to 5 to 6 to 7 to 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Then if we're 22, the next step could only be 22 again or 0. And so we are actually stuck in this like smaller circle, and we know that 500 is outside of that circle. So now how do we actually implement this? So we basically have this, we have to add the strengthening invariant to our, oh, sorry, this is actually about strengthening. Okay, so this is like the way that we do this, this inductive step, basically, if we just did the simple thing where we're just saying, okay, the counter is not equal to 500, and we're trying to show that if the counter is not equal to 500, it can never become 500. So this is what we're doing here. We're saying, okay, the property holds in state 0. state 1 follows state 0, and now does the property not hold in state 1? And it will actually tell us the thing that I illustrated earlier, where basically if the counter is 499, it can be 500 in the next cycle, and the property is violated. Now we add this strengthening thing. So we're basically saying like, oh, we have this additional assertion, and in the Chisel design, you could basically just write another assert. We have this additional assertion that the counter value is always greater than or equal to 22. 22 is always greater than or equal to the counter value. And so that means now we take both assertions together. The assertion that the counter is not equal to 500, the assertion that the counter is not equal to 500, and this assertion that the counter is smaller or equal to 22. And now if we do the inductive step with that, it will actually be unsat. So we're saying like, okay, if this property holds in a step, and then we take another step, then that means that property cannot be violated in the other step. So basically it means we're always staying within that circle. And now the only other thing we have to do is we have to show that the first state, the initial state of the counter, is also within the circle. Because we're saying like, if you're in the circle, you always stay in the circle. So going back to the picture, if you're in the circle, you always stay in the circle. That's what we just proved. Now we just need to prove that we start in a circle. And the way you do it is you just say like, okay, if S0 is the initial state, then this new stronger property holds, then it's in the circle. And so that way we then sort of prove by induction with our base case and our inductive step that we can never reach this value of 500. And in this case, it's just normal, like one induction. But the reason this is called K induction is because for some other properties, you might actually have to reason about multiple steps. So you can say, oh, the first 3 steps, this property holds. And if we assume that for 3 steps, this property holds, then in the next step, the property will also hold. And that's then a 3 induction, basically, where you do 3 steps. But yeah, that's basically then a way that you can circumvent this limit where we're saying like, oh, with bounded model checking, you can only reason about K steps. In this case, if your K induction passes, you actually have proven your property for all possible number of steps of execution of this circuit. But as I said, the problem is if this induction step fails, it can be because there is a bug in the circuit, because your original assertion can actually be violated, or it could be because you need new and stronger assertions to then prove your initial assertion. So in this case, right, we had to add this assertion that count is smaller or equal to 22 so that we can prove it in one step that this original property that count will never be 500 holds. And so that's why I'm saying first do some testing, then do some formal verification with bounded model checking, because bounded model checking will always give you a good counterexample. It will always give you like something you can actually execute in a test if it can find something. And only if bounded model checking says like, I can't find any violation of your assertion in reasonable time, then try to prove your circuit correct. Okay? Are there any questions?
I don't see any.
Okay. Yeah, this K induction thing can be a lot. So, you can look at it at home at some point or like, read somewhere about it. I think it's definitely a lot to wrap your head around. So if you didn't quite get it, that's also fine.
A small question. How about the performance of this K induction? Like if we have 100,000 steps.
Yeah, also bad. I mean, you saw like basically the thing is the stronger your assertions, the fewer steps you need for your induction. And the fewer steps you have for your induction, the more realistic that it will finish, basically, right? But you can have even like a one-step thing that never finishes just because there is something in the circuit that's really complicated for an SMT solver to reason about. Because in the end, even for a circuit that has no state, we still have the problem that this question of whether there is assertion violation input is essentially reducing down to the satisfiability problem, which is NP complete, right? So you can always be in a situation where it will just never give you an answer. But it turns out in a lot of realistic cases, it actually does work, and it's really nice when it works.
Thank you.
Okay. No more questions?
looks clear in person.
Oh, cool.
Well, great. Let's thank Kevin again. This was a fantastic guest lecture. Yeah, I mean, I think that K-Index is kind of a really fun way to kind of show to keep building. I think one of the things of this course I keep trying to tell students thinking about how to use software to make hardware better. You know, we talk about Agile in this course, but just in your case, correctness, right? Like how can we make programs help us do things, right? And so that's really cool.
Yeah, I think the also the Chisel spin to this a little bit is that these properties, for example, this Q property that I wrote, you can think of it as a generator. So there is actually like a library function now in Chisel test where you can just give it your Q ports and will instantiate the trace and like the property and everything, so that it's kind of packaged up for you to use. And so that's also a way to like sort of leverage these like capabilities from Chisel with formal verification, to make it easier to like package up properties for people, because as we discussed, like finding the right property is actually like one of the harder parts of using it.
Sure, that sounds good. Well, thanks again. I'm gonna stop the recording.